usually keep motors running a long time with a minimum of trouble. But eventually, like any piece of machinery, a motor or its load will develop a problem. And when that happens, you've got to be ready. Randomly swapping out parts or taking wild guesses at what might be wrong is not a good way to get a machine up and running quickly. Troubleshooting is a science. To troubleshoot effectively, first of all, you've got to know how the motor is supposed to work, how much current it should be drawing, for example, or how to start it. And it helps if you know the history of the equipment and whether it's been breaking down frequently. Then, to track down the trouble, you must follow a logical, step-by-step procedure. You investigate the symptoms. Based on what you discover, you analyze the problem and list the probable causes. Then you perform systematic tests to eliminate possibilities until you locate the trouble. As we'll see, investigating, listing probable causes, and testing may have to be repeated several times as you keep narrowing down the possibilities. Last, remember that good troubleshooting doesn't end when you have tracked down the problem and got the equipment running again. Try to figure out why the problem occurred in the first place. Can a maintenance procedure or an equipment modification keep it from recurring? You should do what you can to keep the trouble from happening again. Now let's see how this method applies to troubleshooting motors. Usually, when you are called out to work on a motor, it is because for some reason the motor will not run. It's pretty obvious that power must not be getting through the motor. And anyone who has any experience with motors would know that chances are an overload is tripped, a main fuse has blown, or a circuit breaker has tripped, or the contactor to the motor is not pulling in. It is also possible that there is an open in the motor itself or the lines to it. Let's suppose that the problem is an open in the motor. The motor windings have burned out, in other words. Now, this is not normally very likely, so an experienced troubleshooter would not start by checking the motor's windings. What would you do? Well, whether you realize it or not, you have already started on a good troubleshooting procedure by listing the probable causes. Now what you must do is eliminate these possibilities systematically, starting with the most likely. Notice that at first you are looking at the whole machine as a system of components, only one of which is the motor. Your list of causes actually divides the machine into its basic parts. As you eliminate each probable cause, you are also eliminating parts of the system. Now, the most likely cause for a motor not running is a tripped overload. Checking it is easy. Look to see if the overload reset button has popped out. In this case, of course, you would find that the overload has not tripped. Overloads trip when a motor draws too current for too long, not when there's an open and the motor is drawing no current. Now, what is the next most likely cause? Probably a tripped breaker or blown power line fuse. To eliminate these, you would take a voltage reading to see whether power is reaching the contactor. With an open in the motor, you would find normal voltage. This eliminates the main fuses or circuit breakers and everything else that brings power to the starter. Next, you try to eliminate the contactor and control circuit. See whether the contactor pulls in when the start button is pushed. In this case, it would. But let's suppose for a minute that the problem was not an open in the motor. Suppose the contactor did not pull in. How would you continue troubleshooting the system? Well, the probable causes for a contactor not pulling in are either a problem in the control circuit or a bad coil in the contactor. To eliminate one or the other, take a test reading at the contactor coil. Normal control voltage eliminates the control circuit. Since voltage is reaching the coil itself must be bad. If there is no voltage, check the control circuit fuse. If it is okay, the control circuit supply or some switch, sensor, or relay is bad, and you will need to pull the system schematic and trace it through. When you do find that the contactor is pulling in correctly, you must still make sure the contactor itself is doing its job. Check the voltage to the motor on the downstream side when the start button is pushed in. When you find normal voltage, you have eliminated everything in the system except the motor and the lines to it. Now you have to subdivide the only remaining part of the system and test to see whether the open is in the motor or the lines. First, lock the system out and measure the resistance between the lines to the motor. The reading will be high or infinite and will confirm that there is an open downstream. Then take a reading in the motor junction box and compare it to the reading at the contactor terminals. If you get a reading that is much lower, you know that the problem is in the lines. But when you find the same high reading, you know that the open is actually in the motor and you will have to pull it for repair or replacement. The troubleshooting method has led you quickly and directly to the actual cause of the problem with a few simple tests to eliminate probable causes. Now don't forget that good troubleshooting also involves determining root causes. Before you connect up a new motor, you should try to determine why the old one burned out. Check the setting of the overload breakers. They are supposed to prevent motor burnout. Make sure nobody has tampered with them and that they are properly calibrated to protect the new motor. Was the old motor especially dirty, or was it working in an especially hot environment? Talk to the operator or pull the work records on the motor to see if it has a history of tripping its overloads or breaking down some other way. You might also make sure the operator understands the limitations of the motor and has not been overloading it in some way or starting and reversing it too often. Now let's suppose the problem was not an open in the motor, but a dead short to ground in the motor. How would the troubleshooting method lead you to it? Again, the basic symptom would be the same. The motor would not run. And your probable causes and tests would also be the same. You would still start by checking the overloads. Chances are they will not be tripped, since their job is not to protect the motor against this kind of fault. Again, you would go to the voltage on the input side of the contactor. This time, however, you would find no voltage, and this indicates a problem somewhere in the power supply. Now, what are the probable causes? It is unlikely, but possible, that there is no line voltage coming into the main panel. It is also possible that there is an open in the lines to the starter. But by far the most likely possibility is a blown main fuse or tripped circuit breaker. Go to the main panel or breaker box and check. If you find a blown fuse or tripped breaker, it could be because of a one-time condition of some kind, like a lightning strike on the line. But more likely, there is a short somewhere in the system. It is dangerous to just reset the breaker or replace the fuse and turn the power back on. If there is a dead short in the system, breakers can explode. So first, check voltage to make sure the breaker is really tripped. Then, take a resistance reading on the lines out of the main box. If the resistance is high or infinite, and it will be in the case we are supposing, you can replace the fuse or reset the breaker. Be careful here. Even though you are pretty sure you are not switching power onto a shorted line, stand to one side and look away. If the fuse or breaker holds, you can eliminate the lines to the starter and the input side of the starter itself. Now try to start the motor. The fuse will blow or the breaker will trip immediately. This tells you that the short is very likely in the motor or in the lines to it on the motor side of the contactor. Lock the system out and take resistance readings at the motor junction box to isolate the short. Now a short to ground will show up in a resistance reading on the motor, but a short between the windings may not, since a motor's resistance is normally very low anyway. If you cannot identify the short in the motor, try to rule out the lines. Check their resistance to ground and to each other. Infinite resistance readings eliminate them. Again, the troubleshooting method has quickly and directly led you to the problem. Okay, now suppose you find the most common situation, a tripped overload. The most likely cause is that the motor, for some reason, was drawing too much current. The other possibility is that the overload breaker itself is defective. To eliminate one or the other, you'll have to try restarting the motor. When you do, you'll have a useful opportunity to investigate the symptoms further, analyze them, and perhaps save yourself some time and trouble. Make sure the machine is off and reset the overload breaker. Then, once you're sure it's safe, try to start the machine and be ready to observe closely. You will find one of two things happening. Either the motor will start up or the shaft will not turn at all. And in either case, you can analyze the situation and eliminate some possibilities, depending on the type of motor involved. Suppose the motor does start up. If it is a single-phase capacitor start motor, you know that the start winding, the centrifugal switch, and the capacitor are probably okay if the motor comes up to normal speed. You can also rule out the rotor excitation circuits of a synchronous motor if the motor pulls into synchronous speed. On the other hand, if it does not pull into synchronous speed, suspect the rotor excitation circuit. If it is a three-phase motor, you know that all three phases have at least some voltage on them, and any fuses in the lines are good. You know that the motor windings are not open or burned out, if any type of motor seems to run normally. It is possible in that case that you do not really have a problem at all. Maybe there was a one-time condition that caused the motor to draw too much current. But if the motor has been tripping its overloads frequently, you will need to track the trouble down. Watch the motor until the OL trips again. If you hear the motor suddenly load down right before it trips, you have pretty surely eliminated the overload breaker itself. The OL is tripping because something in the load is overloading the motor. You will need to check out the equipment that the motor is driving to discover what is causing it. However, if the OL trips while the motor seems to be running normally, the cause could still be either the motor drawing too much current or a defective overload breaker. The test to eliminate one or the other of these is to measure the current to the motor. Now, most overloads are set to trip when the current draw is 10 or 15% above nameplate current. If you find that the OL is tripping when the current draw is below that level, you have eliminated the motor, the load, and all the rest of the system except the overload breaker itself. Overload breakers trip when motor current heats them too much. If motor current is not too high, something else must be heating the OL and causing it to trip. It could be that ambient temperature inside the controller box is too high, or dirt is preventing free airflow through the box. It could also be that a terminal or connection in, on, or near the OL is loose or corroded and heating up when current goes through it. Still another possibility is that the overload breaker contacts are dirty, pitted, or corroded, and heat from current in their resistance is tripping the OL. Now, if the overload is tripping because the motor is drawing too much current, you can eliminate the overload breaker. It is doing its job. Now you've got to discover why the motor current is too high. Voltage at the motor may be low or high. There also might be a partial short in a motor winding, bad enough to increase motor current, but not enough to keep the motor from starting up. Or something may be dragging in either the motor itself or the load. Dry or worn bearings, bent and rubbing parts, dull cutting tools, or too heavy a load on the equipment, all will increase motor current. The easiest of these probable causes to test for is incorrect voltage. Both high and low voltage can increase motor current. For the motor to run normally, the voltage must be within 10% of the nameplate voltage. Measuring the voltage to the motor at the contactor is adequate in most cases, though it will not detect a voltage drop due to high resistance in the lines to the motor. If measuring voltage at the motor junction box is not safe, you can eliminate a problem in the lines by measuring line-to-line resistance at the contactor and at the junction box. If the readings differ, there is a problem in the lines. With a three-phase supply, all three line-to-line voltages should be equal. Line-to-ground voltages may not be equal, however, depending on the type of three-phase supply. Be sure you know what the readings should be. Many motors are controlled by starters which are supposed to provide a voltage which increases gradually or in steps as the motor accelerates. Determine if the starter is providing the motor with full voltage when it should. If it is not, the motor may draw too much current and trip its overloads. If the voltages to the motor are okay, you have eliminated supply voltage as a probable cause. Now you need to try to eliminate either the motor or the load with tests. The tests depend on the motor type. If you are troubleshooting a three-phase motor, you may already have one important piece of evidence. When you check the current draw of the motor, were the currents in all three lines exactly equal? On a three-phase motor, high current in one phase only usually indicates a bad winding. High current in all three phases means a problem in the load. In a single-phase AC motor or DC motor, all you can do in most cases is to check the motor for shorts to ground. Shorted windings, as we said, probably will not show up. If none of your electrical test indicates anything wrong with the motor, chances are pretty good that you have a mechanical problem in the motor or the load. Check for bad bearings and other possible sources of high friction. Be suspicious of any change or adjustment recently made in the load. Remember that changing a flow control or pressure relief valve setting will affect the motor driving a pump. Any ratio change in a drive will change the load on the motor. And centrifugal blowers may overload their motors if certain ductwork or filters are removed or damper settings are changed. Now, in the case when the shaft does not turn at all and the overload breaker trips quickly, you can assume that the overloads themselves are all right. Again, there are several probable causes. One obvious probable cause is that the shaft is locked up mechanically. The test is usually easy. Will the shaft turn? If it will not, subdivide the probable cause. The jam-up is either in the motor or in the load. Uncouple them and try to turn the motor and the load individually to see which is locked. If there is no jam-up and the coupled shaft will turn, the cause of the problem can vary depending on the type of motor. A single-phase motor that will not start up may have a problem somewhere in the starting circuit. The start winding may be burned out, or the centrifugal switch may not be closing. A capacitor may be shorted or open. Resistance readings should pinpoint the problem. A three-phase motor, induction or synchronous, that will not start up at all may have a burned-out coil. Or one-phase voltage may be zero. Voltage and resistance checks will eliminate one or the other possibility. Be sure you know how the motor is connected internally. An open winding may not show up in a delta motor. A DC shunt motor with an open in the field circuit will probably not start up under load. Now, we have seen how to use the troubleshooting method to pinpoint the cause of a motor problem. But as we said, the troubleshooting process is not finished until you have determined what caused the cause. Some general principles about why motors fail may be helpful before we finish. Most motor problems are associated one way or another with heat. The general rule of thumb is that a motor's life is cut in half by a 10-degree rise in operating temperature above its insulation rating temperature. High temperature causes insulation breakdown and shorts between winding turns or between a winding and ground. Current in these shorts produces more heat, which accelerates insulation breakdown in a runaway process that eventually burns the motor out. In most cases, high temperature in a motor is a result of high current, and as we have seen, high current to a motor can be caused by many things. Mechanical problems in the motor or load which require it to produce too much torque, low or high supply voltage, zero phase voltage, and current leakage through minor shorts. The overload breakers are supposed to protect the motor from overheating caused by high current, but sometimes they do not respond quickly enough. On some equipment, low voltage and phase loss relays also work to protect the motor from damage. But no kind of protective equipment can prevent motor damage in all situations. If dirt prevents heat loss, for example, a motor may overheat without tripping its overload breaker. Whatever you decide the root cause is, take steps to correct it. Perhaps lubrication or other maintenance schedules need to be modified. Possibly equipment alteration or readjustment overloaded the motor. The motor may not have been the right one for the job in the first place. Getting to the root cause can save you a lot of trouble in the future.